Hello everybody. So continuing on with computer science, I wanted to mention in the last video that there is another type of conversion where you have a denary number, for example, and they ask for you to put it in binary, but here the binary is called BCD, and BCD stands for binary coded decimal. Okay, so basically, it's a very easy method. You just take each digit here. So 1, you find the binary number for 1, the binary number for 7, the binary number for 9. So if you have 1 here, you have 2 to the power of 3, power of 2, and so on. Then you can't fit 2 to the power of 3 into 1, so that's 0. Can't fit this data, can't fit this one either because 2 to the power of 2 is 4, and this and this. You can only put into the power of 0 because that equals to 1. So, and then you just do the same thing with the others. This is just another way of representing a denary value. Now, moving on, here I want to continue with section 1.7, text and character sets. So, a character set is a set of all the characters and symbols that can be represented by a computer system. Each character symbol is assigned a unique binary value. What this means basically is that we have, for example, A, it will have a unique binary value that's like 1010, for example. So there are two character sets that are widely used. ASCII, which has two types actually, standard and extended, and Unicode. Now, for ASCII, it's the most basic character set, with having 7 bits used per character, which means that you can have 128 characters. But ASCII only represents the English language, unlike the extended, where it uses 8 bits, which allows you to have 256 characters. It supports more characters like this and so on. But with Unicode, you have 16 bits used, so you have way more characters that can be used, that can be represented. And Unicode is usually used to represent characters from other countries, like from the Arabic language and Chinese language, and emojis and so on. Now, the difference between them is that ASCII has fewer characters, unlike Unicode. It can require up to 16 or 32 bits per character, so that means that you can represent a lot of characters with the Unicode character set. So, going on to the next section here, how is text converted to binary? So, a character set is used, such as Unicode or ASCII. Each character has a unique binary value. We've already discussed this. And yeah, that's basically it. It's a very simple idea going from text to binary. So if I had, for example, the sentence, this is a sample text, for example, each character is 1 byte. Okay? And also the spaces count as a character. So all you have to do is just count the amount of characters, and then that's basically it. Then you just have it in bytes. So going on to the next part. Now here we're talking about representing sound in computers. So computers can't understand sound waves directly since they are analog. So sound must be converted into digital form, which with computers it would be binary. So the process is by using ADC, which converts analog to digital. Okay, and then what we call this recording of sound and then converting it to analog to digital, this part going from A to D, analog to digital, is called sampling. But recording the sound is called a sample. So a sample is basically a recording of a sound, and sampling is taking that sound and turning it from analog to digital. And a sample rate is the number of samples taken each second, measured in hertz. And the last term here is sample resolution, number of bits per sample. So these are going to be important when we begin to calculate the file size for the sound. Now, the higher the sample rate and sample resolution, the better the quality of the recording, the accuracy of the recording. Now, how is analog sound recorded and converted to binary? So, the analog sound is recorded using a microphone. Okay, and this recording of sound is a sample. The sound wave is sampled, measuring its amplitude. Each amplitude has a unique binary value. Okay, so before we continue, amplitude is the height of the sound wave at a certain point in time, and it tells you how loud the sound is at the moment. So for example, it would look like this. This would be the amplitude. Okay? So then this amplitude, when it gets sampled, it gets assigned a unique binary value. Each measured amplitude must be stored as a number, and computers only understand binary, right? So each amplitude is converted into a binary number, and that's basically what they mean when they say each amplitude has a unique binary value. So whatever number they have here on the amplitude is y-axis, okay? This number gets converted into a binary number, okay? Now, sample rate is important when converting to binary because the fewer samples you have, the less detail or the less the sound quality becomes. So you would feel like the sound is distorted. On the other hand, if you have a high sample rate, that means there are more samples, which means smoother, a more accurate digital version of the sound. So, and the sample resolution also affects the sample resolution also affects the conversion with the same idea. So you have here that sample resolution means the number of bits per sample. So the less bits you have, right, the fewer amplitude levels that you would have, which makes the sound rough or distorted, right? But it's the opposite with high bit depth. If you have what I mean by high bit depth is that you have more bits per sample, which makes it smoother and more accurate. Now, we're gonna start with image terms. Let's see here. Pixels are one square in an image that has one color and the smallest component of an image. Okay? So resolution is the number of pixels per inch, the number of pixels wide by the number of pixels high, and the number of pixels in an image. Okay? Color depth is the number of bits used to represent a color. So to get the number of colors in an image, you would have to do 2 to the power of the color depth. Okay? So the file size and quality of the image increases as the resolution color depth increase. Now, you have to keep in mind that the fact that the file size is increasing is a disadvantage of increasing resolution and color depth. But an advantage would be an increase in quality of the image. Now moving on, how is a digital image converted to binary and stored on a computer? So now we're gonna see how it's converted to binary, and it starts off where you have an image is made of a series of pixels, okay? Each pixel stores one color. Image has a set number of pixels wide by a set of pixels high. Each color has a unique binary value. The binary value of each pixel is stored in sequence. Files contain metadata to identify how the file should be displayed. So what this is basically saying is that you have an image and it's a series of pixels. So it has a lot of pixels, right? Each pixel stores one color, and a color has a unique binary value. So basically what they do, they just put the colors, they convert it, they take the binary value, and they put it in sequence. That's it, basically. And metadata just means extra info. And here they say that it can be the color depth, okay? Don't forget, color depth means the number of bits used to represent a color. Now moving on, here you have to memorize the conversions, and that's basically it for this section. Just memorize the conversions and make sure you know that a byte is 8 bits and that a word is 16 bits and so on. Now we're gonna start with calculating image file size. An image has a resolution of 1000 times 1000 and a color depth of 2 bits. Calculate the file size of the image. Give your answer in bytes. Show your work. Okay. So first you have to know the formula. And the formula here is the height times the width times the color depth. So here they already gave you everything. All you have to do is just substitute it. So 1000 times 1000 times 2, right? But the answer that you get is in bits, and they want it in bytes. So to convert from bits to bytes, you divide by 8, and you get your answer. Now here in this question, instead of giving you the information, they showed you the image. So the first thing you have to do is find the number of pixels. Now, the way you could find it, just by finding the number of pixels here and finding the number of pixels here and multiplying them, and you get here 56. Okay? Second step is find the number of bits needed to represent each pixel. So we know that the formula is 2 power of color depth equals to the amount of colors, which in this case is 5, because we also include white. Don't forget about white. So 1, 2, 3, 4, 5. Those are 5 colors. So 2 and equals 5. The n, which here would be the color depth, would be 3 bits. Now why do we take 3? Because 2 to the power of 2 is 4. But 4 is less than 5. So instead of doing 2 to the power of 2, we're going to do the one, you're going to use the one that has a bigger value. So in this case, you're going to take 2 to the power of 3, not 2 to the power of 2. So if you had, for example, the same idea, like you had 2 to the power of n, we're trying to find the color depth, and equals to 7, and you have 2 to the power of 2, 2 to the power of 3, you take 2 to the power of 3. Now, the last thing you have to do, now you got your color depth, and you know the width and the height. You just multiply everything together. The width and the height, when you multiplied it, you got 56. So you just do 56 times 3, you get 168 bits, and they want it in bytes. so you divide it by 8. Now here we are asked to calculate the sound file size. Now the formula for this is the length of the soundtrack in seconds times the sample rate times the sample resolution. So in this question, they told you that music is sampled 48,000 times per second. Now what is this? This here is the sample rate, okay? Each sample is 16 bits. This is the sample resolution. And each song is 4 minutes long. Here you have to know that it's always in seconds, so you're gonna take this and you're gonna multiply it by 60, right? So once you do that, you just multiply all your numbers and you get you get a big number. Keep in mind though that they said that for a stereo sound, 2 separate paths of sound are required. So it is necessary to sample twice. Basically, whenever they mention the word stereo, you should know that whatever numbers you have, when you multiply them by 2, okay? And then the last thing they want is for you to convert to MIB and you get 43.94, okay? So the basic idea is that you have to make sure you have the sample rate, the sample resolution, and the length of the soundtrack to be in seconds. And whenever they say the word stereo, for a stereo sound, you should multiply your answer by 2. Now, I think the most important thing here is to definitely memorize the conversions, because when solving these questions, maybe you might have gotten the right answer, but you didn't convert or you don't remember the conversion. So make sure you guys memorize this. Now, going on to the last section of chapter 1, file compression. File compression refers to changing the file structure to decrease its size. Its advantages are less storage space when saving the file, less time will be required when uploading/downloading the file, less bandwidth required for transmission, and reduces the cost of cloud storage. What they mean by this last point here is that smaller files take up less storage space on the cloud. And since most cloud providers charge based on how much space you use, storing or compressing files cost less. And also, bandwidth here basically means the maximum amount of data that can be transmitted through a communication channel, so like the network or an internet line. Now there are 2 types. You have lossy compression and lossless compression. Lossy permanently removes unimportant or redundant data from the file being compressed. So when you compress the file, it takes the unimportant data or whatever they think is not important and removes it permanently, so you can't get it back. Once the file is compressed, the removed details are permanently lost, and cannot be restored. Image, sound, audio, and video files are compressed using lossy compression. Now with lossless, you do not permanently lose this data that you remove, but you can bring it back. So permits the restoration of or the original file upon decompression, used when it is necessary to maintain an original copy of the file. So if the original copy was important, then you would use lossless compression. And lossless compression is used with text files, and programs are usually compressed using lossless compression. Now the way that lossless compression works is that, for example, here you have this text and it has red, green, yellow, green, and so on. What it would do is take, for example, the repeated words, right, and put an index for it, right? So we'd say red has an index of 1, green has an index of 2, yellow has an index of 3, and then it would replace the word with its index. So we said that the index of red is 1. So in the places of red, you will find 1. Okay? Now, this allows for the text size to go from 91 bytes to 41 bytes. So you can see it definitely has a significant difference when it comes to compressing the file. Now, with a lossy compression, they use a compression algorithm. It removes any unnecessary sounds, for example, from like an audio. It would remove sounds like background noises that maybe you wouldn't even notice if it gets removed. And they would use perceptual musical shaping, which is the process of removing low sounds in order to make a file size smaller. So yeah, exactly like what I said. They would remove things that are barely noticeable, low sounds, to make the file size smaller. And these sounds are deleted permanently. They could also reduce sample size and reduce sample rates, and all of this data would be permanently removed. Now, the last thing to mention is you have to memorize the types of files and whether it's lossless or lossy compression, if it uses lossless or lossy compression.